This is the internal energy lesson, lesson 3 in a thermal physics topic. Today, these are the learning outcomes you should be able to do at the end of the lesson once you do the quiz. So first of all, what would absolute zero look like? You would have looked a couple of weeks ago at absolute zero, and it's the idea that that is when a substance has got no motion of its particles. It's the coldest possible temperature something can be. When something's at absolute zero, the particles have no kinetic energy. But to think about what it would look like sort of in total, we need to think about this idea of internal energy, not just kinetic energy. Now, internal energy has a definition which is this. Make sure you learn it. It's a very common exam question. It's the sum of the randomly distributed kinetic and potential energies of atoms or molecules within the substance. Randomly distributed bit, this bit just means that these kinetic energies and these potential energies are distributed along a curve. And they're sort of randomly distributed around that curve, but there is there's a probability curve that tells you what the kinetic and potential energies might be. Don't worry too much about that. But it's the fact that internal energy is the sum of the kinetic energies of the particles and the potential energies of the particles. The kinetic energy is the motion of the particles. That's how much movement energy the particles have got. And temperature is actually a measure of the average kinetic energy of the particles. That's what temperature is. When we say that something has a higher temperature than something else, it means that the average kinetic energy of the particles is higher. So temperature measures the kinetic energy. And then the potential energy, well, we can think of that as sort of the separation of the particles. And I've got an analogy to make that clear for you. And it's going to tell you whether or not gases, liquids, and solids have a higher potential energy. And it's going to also tell you what happens when things change state. So this is our heating curve for water. I'm going to be heating up water in its 3 different states. We're going to start off with water as a solid, as ice, and then we're going to go to liquid water and then water vapor. And what I want you to imagine is we've got a beaker in my lab, and in that beaker we've got a load of ice, and underneath it we've got a Bunsen burner heating it up. We've got a thermometer in there, and we're going to measure how the temperature changes when I heat it. Well, this is what I would get. What happens is the ice starts to increase in temperature, and then at B something happens, and it stays the same temperature. Even though I've got the Bunsen burner underneath it, it's not increasing in temperature. Temperature then increases again, and then at D it stops increasing in temperature, and it stays at the same temperature, even though I'm still heating up, I'm still giving it energy. And then from E to F it starts to rise again. So what happens at B and at D? Well, at B and D, it changes state. At B, it goes from being a solid to a liquid. So from B to C here, it's changing state. The energy that you're giving it from the Bunsen burner isn't increasing the kinetic energy of the particles. It isn't increasing the temperature. It's increasing the potential energy by making it go from solid to liquid, where the particles separate very slightly. Then I keep on heating it, and now my liquid water gets hotter and hotter and hotter, until eventually at D, it then starts to change state to become water vapor. And here, the temperature stays the same, because the energy from the Bunsen burner doesn't go into the motion of the particles, doesn't go into the kinetic energy of the particles, it goes into increasing the potential energy of the particles, moving them further apart. Particles in a gas are much further apart than particles in a liquid. And then E to F is where you're heating up the water vapor. So why does temperature increase at A, C, and E? Well, that's because I'm heating it and it's staying within a certain state. It's staying as a solid, it's staying as a liquid, it's staying as a gas. Why does temperature remain constant at B and D? Well, it remains constant because it's changing state, which means potential energy is increasing, not kinetic energy. And kinetic energy is what temperature is, basically. Temperature is a measure of the kinetic energy of the particles. When does the internal energy increase? Well, internal energy is increasing all the time. I'm always increasing the internal energy of the water. I'm always heating it. I'm always increasing its internal energy. It's just that here, the bit of the internal energy that increases is the kinetic energy. Here it's the potential energy. Here I increase the kinetic energy. Here I increase the potential energy. Here I increase the kinetic energy. But remember, the internal energy is the sum of both of those parts. It's the sum of the kinetic and the sum of the potential. So internal energy is always increasing. And when does it remain constant? It never remains constant. You can try the challenge now, or you can wait until I get to that bit later. I'm going to explain that in a bit. So internal energy is partly made of the kinetic energy, the motion of the particles, and it's also of the potential energy. This is an analogy I quite like. This is the one I was talking about. So here we've got the Earth, here we've got Mr. Miles on the surface of the Earth, and here we've got me living out my dream as an astronaut, very far away up in space. So who's got the strongest attraction? What's the order of strongest attraction? Well, Mr. Mile is closer to the Earth, so he's going to have a stronger gravitational attraction to the Earth. I'm very far away, so gravity is going to be weaker over here, so I've got less attraction to the Earth. However, who's got the highest potential energy? I do. Think about the equation GPE equals mgh. I've got a higher height, so I've got more gravitational potential energy than Mr. Mile does. So I have more potential, Mr. Mile has less potential. Think about that now, relating to the ideas of gases, liquids, and solids. Which has got the order of strongest attraction between particles? Well, solids have got the strongest attraction between particles. Liquids have got a lot of attraction between particles, but not as much as solids. And gases have got very weak attraction between particles. But which has got the most potential? Well, it's the flip of that, the same it was in the gravity example. Gases have the most potential because they have the most potential to come together, to be brought back together. Liquids have a bit less potential energy than that, and solids have the least potential energy. Now, if you look this up in your textbook, there might be a bit that confuses you here, because what it says is it says that electrostatic potential energy is lowest in solids, higher in liquids, and at its highest in gases. That's what we agreed upon. We just saw that here. We're happy with that. That's our order. But how is it highest in gases when it's 0 joules? Well, it's because in solids and in liquids, we define the electrostatic potential energy as being negative. So here you can see in a solid, the electrostatic potential energy has a large negative value. If this is a very large negative value, let's say minus 1,000, 0 is higher than minus 1,000. I know it's a bit confusing, but you'll see why we do it like that once we do fields. So going back to our heating curve for water, we can think about what happens to the internal energy at each point. Well, at A to B, the internal energy increases because kinetic energy increases. At B to C, the internal energy is increasing because potential energy increases. So its internal energy is always increasing because the two different parts of it are always increasing. So what is happening to kinetic energy during each stage? Kinetic energy increases between A to B. B to C, kinetic energy stays the same because temperature is the same. C to D, kinetic energy increases. D to E, kinetic energy stays the same. E to F, kinetic energy increases. What's happening to potential energy during each stage? Well, potential energy increases here, and it increases here, but it doesn't change here, here, and here. Once you've added all the details of this lesson to your notes, please make sure you do the quiz.